non-commutative resolution of singularities. What should a non-commutative resolution of singularities be?
Thanks, Sue. And thanks to everybody for coming. Thank you to the organizers for the opportunity to speak and for the hard work of putting this together. It's been great so far. So the first thing I have to tell you is that Sue told you a small lie, not intentionally, I'm sure. I'm not going to tell you the answer to this question. The truth is that there is no accepted answer to this question. I'm going to give you a walk toward one possible answer that I like. That's about the best I can say in terms of answering the question. So to get started, let's remind ourselves what a usual resolution of singularities is. And let's just stick to varieties. So of a variety, say, X over some field that I won't talk about at all. It is a morphism. I'm going to always write it as pi going from Y to X. Such that, and let me put this back here, I'll try to keep this one. If I start to erase this one, holler at me, because I don't want to lose it. So, and I want to do these in the right order. So first, pi is birational, which I'm going to be pretty informal about and just say it's an isomorphism on function fields. Second, I'm going to say pi is proper, which, again, I'm going to be informal about and not define, but I'll tell you that, for example, projective works, or also finite morphisms are proper. Come back to that later. And finally, of course, the important thing is that Y should be non-singular. It should be smooth. So, of course, there are many, many well-known applications of resolutions of singularities. For example, if you want to compute cohomology over your singular variety, you somehow compute cohomology over the Y, the non-singular thing, and try to push it down. I'm not going to get into these too much, though I will say a couple of things at the end. What I want to do instead is complain about this definition. So here are a few petty complaints about this definition, which basically boil down to complaining that geometry is hard, and I'm a commutative algebraist. So these are the complaints of someone who was raised, my mother's milk is commutative algebra, and trying to learn geometry is, well, makes my head hurt sometimes. So for example, petty complaint number 1, again, let me do these in the right order. So as I said, I'm a commutative algebraist. So my first complaint is that if I am handed an affine variety, which for me is a synonym for ring, the result is probably not affine. So suddenly I'm no longer doing commutative algebra, which is, I could stop the talk here. Really what they are, if, say, X is spec R, we end up looking at Rees algebras or Rees rings. But in fact, worse than that, we don't even look at the entire spectrum of such things. We look at just the proj. So instead of my beloved dictionary that allows me to go back and forth between, say, regular rings and non-singular varieties, now I have to worry about this thing being maybe regular on the punctured spectrum or something like that, which is complicated. Also, Rees rings, as we heard from Young Soo yesterday for 5 minutes, can be pretty badly behaved. They can have very low depth. They can be hard to work with. So I complain. Second complaint. It's known to exist, that is, a resolution of singularities is known to exist in characteristic 0 by, of course, the famous work of Hironaka, which isn't a complaint. The complaint is that, again, geometry is hard. This is a very hard proof. Specifically, let me make a precise complaint. It's known that if I have an affine variety, then the resolution of singularities is, in fact, proj of a specific Rees algebra. But because Hironaka's proof is so densely recursive, with, I think, 17 nested recursions or something like this, there is, as far as I can tell, no algorithm to produce the single ideal that gives you the resolution of singularities. You can produce an ideal that resolves a little bit, and then another ideal in those charts that resolves a little more, but to get the actual I, there is no algorithm that I know of. And third, this is the last one. Given the trend in so-called modern, well, not so-called, I'm going to call modern algebraic geometry, to focus on the categories, say, for example, coherent sheaves on X or quasi-coherent sheaves on X, or say the derived bounded derived category of one of these, which we heard about again in one of the 5-minute talks yesterday, if you were here, from Adam, I think. It would be very nice to be able to control the effect of a resolution of singularities on these categories. Under pi. And there are, in fact, some very precise conjectures for what the effect on some of these categories, particularly the bounded derived category, should be, but mostly this is just whining and complaining, so I don't have to give you particulars. So to address the first, maybe we're making life too hard for ourselves. I do this all the time. Maybe it's possible that we could resolve singularities in some way that actually gave us back an affine variety if we started with one. It's a nice hope. Since I'm being naive, I'm allowed to make naive hopes. Of course, the very first example, well, maybe the second, this, it's very easy to see that, well, let me write it differently. the quotient by that has no, say, module finite, because that's what a proper morphism is between affine varieties. Module finite regular birational algebras. So if you were, as I am, a pure commutative algebraist, at least I play being one on TV, you are out of luck. You cannot resolve singularities by doing only commutative algebra. But maybe we can combine this third complaint with the naive hope in the following way. Let's say it like this. If we focus on derived categories, the bounded derived categories, either coherent or quasi-coherent sheaves, whatever you like, then we know from Ricard that let me say it like this. The bounded derived category is invariant under Morita equivalence. So in particular, the bounded derived category of modules over some ring, say finitely generated if you like, is equivalent to the same category of n by n matrices over that ring, just as an example. And what I interpret this to mean is that the derived category is blind to commutativity. It can't tell if you handed a ring whether it's commutative or not, because you might have handed a commutative ring or you might have handed it this thing, which, as we heard from James Zhang's talk this morning, is never commutative. So perhaps we can rescue, rather than expanding our world to encompass varieties that are, say, projective over an affine scheme, something that you usually get when you do a resolution of singularities. Instead, let's expand the other direction. So let's try to rescue that naive hope by allowing again, we'll stick to module finite algebras, as we tried to above. But now let's allow the target to be a Greek letter, that is, to be non-commutative. And we probably should insist on R going into the center just to make things sane. So that's the starting point to get to the question. What should a non-commutative resolution of singularities be? That is, what should we ask from one of these not necessarily commutative algebras in order to entitle it to be called a resolution of singularities? Well, I'm not erasing this. Oh, hello. That's all right, I'll just pull, I don't need to write down that anyway. It's just a little flashback. So let's mimic the 1, 2, 3 from above. So the first thing we asked for in the usual case was that it's birational. So I'm going to write here birational. But so what isomorphism on function fields? So I could ask that this extension R to lambda be such that if you take lambda and you tensor it up to k, where k is the quotient field of R, that you get k. That's what birationality means up here. Of course, this is ridiculous. There are no honest non-commutative algebras that do this. This would be to get you back to the situation we decided had failed. But we've already decided that what we want, or what we would like, some sort of statement about derived categories, can't distinguish between k and things that are Morita equivalent to k. What are Morita equivalent things to k? They're only the matrix rings. So we ask that when you tensor lambda up to the quotient field, you get some matrix ring over the quotient field. All right. Second, proper, I said I wasn't going to tell you much about that, and I'm not going to talk about projective either, but module finite I think we've established is going to be good enough. So let's say we assume it's module finite. That is, that lambda is a finitely generated R module. And third, non-singular, well, that's, again, we've learned what that should mean in the first talk this morning. So we assume that the global dimension of our algebra is finite. So this is our first attempt, first steps towards answering the question. I'm really grateful to James for giving the talk that he did, because he explained exactly why this is a terrible idea. Well, not terrible, but insufficient. Once you allow your ring to be non-commutative, you lose most of what makes non-singularity useful in the usual situation. You lose, well, ring theoretic point of view, you lose Alexander-Buchsbaum. You lose the relationship with Kroll dimension. You lose even being a domain, this conjecture of Ramras that we heard about this morning. You lose everything. So we need something a bit stronger. So to avoid this bad behavior, rather than trying to strengthen the property, though I'll do that too, I want to just restrict to the rings that I allow. Restrict both R, well, and lambda in a second. So here are the new assumptions on my ring R, which has had essentially no assumptions so far. That should have been a sign that it wasn't quite going to work. So I'm going to assume, again, the right order, that our ring R is sort of the most, well, let's just assume that it's a Cohen-Macaulay local ring. That's really the minimum we should expect to be able to deal with. And in fact, in a minute, it's going to be Gorenstein. So this is a well-behaved class of rings, but it still includes plenty of examples that people find interesting. Plenty of examples. So for example, rings of invariance. Rings defined by determinants, certain determinants. Hypersurfaces. Make sure to list that separately because it's important later. So this is the base ring. And it's not such a big restriction, I don't think. Here's a bigger one. Let's assume, now here's an assumption on lambda on the algebra. That lambda is an R order, which is a bit of unfortunate terminology. If you looked at this line, you might have thought, oh, classical orders, maximal orders, things like that. No, this is different. Those are coming later. What I mean here is that it is maximal Cohen-Macaulay. Sorry, I'll spell that out. Maximal Cohen-Macaulay as an R module, which, if this is not familiar language to you, there's the easiest way to define maximal Cohen-Macaulay as an R module is that it should be free over a polynomial subring. At least if R is graded or complete, this is a reasonable definition. If it's, well, that's good enough for us for today. And third restriction, this is another assumption on lambda. Instead of, well, I guess I said we wouldn't strengthen the finite global dimension assumption, but in fact that's exactly what I'm going to do. Instead of just assuming finite global dimension, which, as we heard this morning, can take on all sorts of funny values, let's assume that it's exactly the Krull dimension of our base ring R. This property is sometimes called non-singularity. So, things are coming in threes today. I had 3 parts of the definition, 3 complaints, 3 bullets. Oh, rats. The following are equivalent. 1, 2, 3, 4. Nuts. Oh well. So, with these assumptions in place, we get what I might want to call satisfactory behavior. So let me give you an example of what means satisfactory to me. Let's just call this a proposition. The following are equivalent for R and lambda as above. First, well, sorry, let me say this differently. The following are equivalent for R, Cohen-Macaulay, local. No, R Gorenstein. And lambda and R order. So first, that the global dimension of lambda is equal to the dimension of R. That's this non-singularity we talked about above. Second, that it's at most the curl dimension of R. Third, it's not quite equivalent to the global dimension just being finite, but it is equivalent if you add an additional condition, which is that what you might want to call the canonical module of lambda that this thing is lambda projective. So this is sort of a Gorenstein condition on lambda. And I'm going to leave off 4 just for the symmetry. It wasn't very important anyway. Also, and let me just continue that thought. Yeah, okay. Things like the Auslander-Buchsbaum formula hold in these cases. So if you are willing to assume R is a little more than the base that you might accept, but is in fact Gorenstein, and you're willing to assume that lambda is an R order, you get back the nice behavior of finite global dimension, at least to some extent. So, drum roll, please. Here it is. Here is a definition. We'll just put all the pieces together, and we'll get a definition of a non-commutative resolution of singularities. A non-commutative resolution of singularities of a Gorenstein local ring R is an R algebra which is first birational in this sense up here, in the Morita invariant sense. Secondly, modulo finite and thirdly, non-singular. So there it is. End of talk. 20 minutes extra for, no, they don't put out more tea. Rats. All right, we'll keep going. The problem, well, there are many problems with this. One problem with this attempt at a definition is there just aren't very many examples. There are some, and I'll talk more about one major source of examples in the workshop next week. But, and I needed to make a couple remarks. Sorry, remarks about this definition. It's very important. The first remark is extremely important. So first, this is a non-standard definition. If you were to stop someone on Telegraph Avenue and take them by the hand and ask them, what is your definition of a non-commutative resolution of singularities, they would be very unlikely to give you this. If they did, well, then they're probably sitting in the third row, sort of near this end. That's about it. In fact, this is nobody else in the world but me would call this a non-commutative resolution of singularities. But we're just going to go with it. The second thing is, I did go ahead and assume that R was Gorenstein. You don't have to. You can just as easily define it for Cohen-Macaulay local rings R, or even drop Cohen-Macaulay if you're feeling especially wild. But it's just not as well behaved. This proposition, for example, is just false. If your ring is not necessarily Gorenstein. So those are the remarks about the definition. Now, as I said, there is a certain paucity of examples. So in order to go a-hunting for examples, let's strengthen the definition. Yes? Yeah. Yeah, of course, I'm sorry. Yes. No, it's there. Can you see it? No. Non-singular doesn't include order. Greg's right. I just didn't write it. Thank you. Sorry about that. And in fact, I just wrote the wrong thing entirely. Module finite is contained in R order. It should have been R order instead of module finite. Rats. All right. So let's go looking for a stronger definition in order to find more interesting examples. To do that, let's go back to geometry, back to the usual resolution of singularities. A very strong condition on such things is that they be crepant. Which is a pun, of course. There's a certain quantity called a discrepancy, and if you have no discrepancy, then you are crepant. But what it means is that if you've got pi from y to x, and you look at the canonical sheaf, sorry. What am I doing here? I'm pushing down. No, that's backwards. I'm sorry. This is what I want to say in a second. Pulling back, I knew it was right to begin with. If you pull back the canonical sheaf for x, you get the canonical sheaf for y. The difference between those things is the discrepancy that I mentioned a minute ago. So this comes up in, for example, the minimal model program and lots of applications that are really a subject of a whole other talk and probably a series of talks. But for me, again, as a simple-minded commutative algebraist, what this means for me is that induction and co-induction coincide. So what I could do is, if I've got the canonical module for x, I could tensor it up over OX to OY. Or I could take HOM. And what this says, since this one really is omega y, the definition of Crepin says that these two things match. Again, I have to say informally because that tensor product is not the right thing. But if these were, say, rings, as they should have been all along, then that would be true. In particular, if the canonical sheaf, the canonical bundled, well, sheaf, downstairs on X is the structure sheaf, so this is some sort of Gorenstein condition. This one, of course, is just O of Y, and this one is, we had a name for this before, it was the canonical module. So this says that if you co-induce the structure sheaf up, you get the structure sheaf back on Y. This has a ring theoretic name. An R algebra, say lambda, is symmetric if HOM over R lambda R, oh my goodness, is in fact lambda. Has bimodules. This has both left and right lambda structures. So this hints that perhaps we might get an analog of Crepin resolutions if we throw this condition in. So let's do that. So a non-commutative Crepin resolution of a Gorenstein R is an R order lambda, which is non-singular. And here's this additional thing, symmetric. Long? Oh, sorry, I thought you had. So, the first sign that this is a reasonable idea is that we have a great source of symmetric algebras. Which is that if R is a normal domain, then the endomorphism ring of a reflexive module is a symmetric R algebra. So, and in fact, it's much better than that. Really, the truth is that state a theorem to this effect. Really, the truth is that from this definition, it follows that a non-commutative Crepin resolution is an endomorphism ring. So let's call this a theorem. This is this is sort of combination of a whole bunch of work. It's due to people like Auslander and Goldman, EMI and Wrighton did a piece. I'll point out which piece in a second. And also an old paper of Brown. Oh, perfect. I have wanted to know for years. How's it pronounced? Hadjarnovus? Excellent. Hadjarnovus and McEachin. It says that the following are equivalent for R Gorenstein and lambda module finite. First, lambda is a non-commutative, Crepin, missing word there, Crepin resolution of singularities in the sense over on the far left. Secondly, it is an endomorphism ring of a reflexive R module and is non-singular and is an R order. So remember what these mean. Non-singular means it has finite global dimension equal to the Krull dimension of R, and R order means that it's maximal Cohen-Macaulay as an R module. Third, that it's an endomorphism ring for a reflexive module, and all the simples have projective dimension equal to the dimension of R. So this last property is called homological homogeneity. So 1 was the definition that I gave. 3 is the original definition of this concept. Due to Michel Vandenberg in 2004. And the fact that 2 and 3 are equivalent, that's the Brown-Hadjarnovus McEachin result. And the fact that 1 and 2 are equivalent, given this definition that I gave there, is the part where the maximal orders and the classical orders come in, but I have to skip over this for time reasons. So, anybody can make definitions. Let me tell you one reason why you should think this is a good definition. And then I'll give you some, and whatever time's left, I'll give you a couple of open problems. So, it is a well-known fact among people who know such things that if you have a crescent resolution as on the board immediately above, then, and X is Gorenstein. Then X has rational singularities. So one piece of post hoc motivation for the definition here is the following result of Stafford and Vandenberg. If R is Gorenstein, and has a non-commutative crescent resolution, then R has rational singularities. And this is from 2008-ish, I think. Yeah. So we're at least not too far off the right track. All right. In the last 2 minutes, let me tell you a couple of remaining open questions. Well, probably just one, probably just half of one. Let me just say something instead of writing it down. As I understand it, Vandenberg's original motivation for this definition here was a conjecture of Bondel and Orlov. To the effect that, and I'm going to state this imprecisely, crescent resolutions of singularities, the geometric kind, the usual kind, sorry, let me say this a little less informally, and so as it makes just a little bit of sense. Two crescent resolutions of singularities of the same variety X have equivalent bounded derived categories. The idea is that these crescent resolutions, the ones satisfying this condition on the canonical sheaf, are very close to the thing you're resolving the singularities of. If you've got two of them, they're both very close, and they should have equivalent bounded derived categories. And so Vandenberg in 04, this is okay for the dimension of X being 3 and having terminal singularities, a mild condition on the singularities. And so the open problem then is, and so the way he did this was, of course you're right, I'm sorry. So this was, it was Bridgeland's proof, or Bridgeland's result, Vandenberg's proof of it again. Thank you. That's what I get for trying to hurry. And Vandenberg's method was showing that the bounded derived category of one of those y's was in fact equivalent to one of these non-commutative resolutions of singularities, and thereby transitively getting the conjecture of Mundell and Orlov. And so you might want to know, are all Crepant resolutions commutative and non-commutative derived equivalent? For example, there's been work on this by Iema and Weems, who showed that all of the non-commutative ones are derived equivalent in dimension 3. And I think that there isn't much hope of this being true in dimension bigger than 3, but I don't believe it's known even then. So I've gone just a couple minutes over. I apologize. Thanks for your time.